What do you think about when you think about a solution?
Contact solution.
Okay, like contact solution, good. Right? The stuff you put your contacts in overnight. What other things do we think of? Do you think of a solid liquid or a gas?
Liquid.
A liquid, good. Typically we think of solutions as liquid, which I would agree with. Are solutions just one thing?
No, a mix.
It's a what?
A mix of things.
It's a mix of things, right? It's typically a mixture of things, okay? And it's a specific type of mixture. Do you remember what type of a mixture it's called? And let's figure out what are the things here that we see that are solutions. Okay, is there anything up here that you see that is a solution?
Windex.
Windex, good. Why is it a solution? It's got more than one thing in it. What else is a solution?
Oil.
The oil, good. And what else?
The makeup forever.
Okay. What about this one? What's this?
Water.
Is water, is that a solution? No, that's what we call is a pure substance, right? It's not a solution, it's just a pure substance. And then what about grass? A solution?
It's not liquid.
No. It's not, it could be a mixture, right? It's a mixture of lots of different types of grass. It's a mixture of grass and dirt, right? But it is not a solution. So let's figure out what makes a solution a solution. A solution is a homogeneous mixture. So that means it's the same. Okay, the same throughout. That's what it means. Homogeneous means it's the same throughout. So every part of that solution looks the same. Things aren't floating on the top or like sinking to the bottom, right? Things are the same throughout. That has to be a solution. The dissolved substance is completely dispersed throughout the solution. So if I would draw out a sample of my solution at the top and at the bottom, they should have the same concentration. What do you think of when I say the word concentration in terms of solution? It's kind of hard to describe without using the word concentration.
The barest part of it or something?
Kind of.
The non-diluted.
Okay, good. A non-diluted something. When I say concentration, it's a measure of how much stuff has been dissolved in that liquid. Right? So if I make chocolate milk, right? Do you ever make chocolate milk with the syrup? Okay, or the powder, whatever. But with the syrup. Okay, so if you make chocolate milk and you only put a little tiny bit of syrup in, it's not very concentrated, right? My solution is not very concentrated there. There's not much solute being dissolved in our solvent. But if I make chocolate milk and I pour tons and tons of syrup in, right, then it's really concentrated. It has a lot of that solvent, whatever it might be. Okay, does that make sense? Same like if you start out with, for example, if I give my kids apple juice, I might put a little bit of apple juice and a lot of water, right? I'm diluting that concentration down so that it's not so sugary, right? Those are the things we're talking about when we look at concentration. Okay, typically solution is a solid that's been dissolved in water, but it could be liquids dissolving, guys. Could be liquids dissolving in other liquids or a gas dissolving in a liquid. Can you give me a scenario in which we might see a gas dissolved in a liquid? Any thoughts on that? I only really can come up with one example. That's like if you have beverages that are carbonated, right? The gas bubbles are evenly dispersed throughout the liquid for a while, and then eventually they separate out, right? But that would be an example of that. All right, so in a solution, we have really small particles that are evenly distributed. In theoretically, a solution will not separate. Okay, so let's think about what we mean by that. Have you ever made Kool-Aid before?
Yep.
Right. What do you have to put in the Kool-Aid?
Sugar.
You have to put sugar and you got to put the mix, right? What happens if the Kool-Aid sits in your fridge for too long?
It's hard.
All of the sugar does what? It falls to the bottom, right? That would be a separation. What would I need to do to get it to be a solution again? I just had to stir it back up, right? Get those particles to dissolve again. So it's not a solution if it's separated. Now that becomes a heterogeneous mixture. There's multiple parts to it, okay? These are a couple vocab terms we need to know. The solvent is the substance that's doing the dissolving, and the solute is the thing that is being dissolved. So in our next example here, which is which? Which is the solute? The Kool-Aid or the water?
Kool-Aid.
Kool-Aid is the solute. Water would be called the solvent. Okay, so typically the liquid is the solvent. And then the solute would be a solid most of the time. Oops. Okay. All right, that's just kind of restating what we said there. Typically the substance in greater proportion, so the thing there is more of is the solvent. The thing that we have less of is the solute. So here's kind of the overview of what happens in a mixture solution, okay? If we want a solution to happen, the solute particles must separate. So let's envision, guys, let's envision the Kool-Aid process again. Okay, we have got Kool-Aid powder and we've got sugar that's being put into water, agreed? So when I pour those things into my water, those Kool-Aid particles have to separate and the sugar particles have to separate. Right? In order for it to become a homogeneous solution, those things have to separate. That step requires energy. The solvent particles must separate. This process requires energy. So that means our water particles are kind of spacing apart to make room for those Kool-Aid and sugar particles. Right? They're kind of making room. The solute and the solvent particles attract. That process releases energy. So I want us to think about the first two steps here, where these particles have to break apart. Okay? If they have to break apart, what are some other ways that we can encourage the dissolving process? Okay, I want you to just think about, with the person next to you, I want you to discuss what are one or two ways that we can encourage the dissolving process. We can input energy to encourage dissolving. Okay, talk about it with the person next to you and let's see if we can come up with some things. What can we do to encourage dissolving? The dissolving process, what do we think? Stirring, good. What else?
Heat.
Adding heat, good. Shaking it. What else? Those are the things we all came up with. Did everyone think of heat? Right? Typically we heat things up to try to make them dissolve better. What else? Okay, let me ask you this. If I want to make salt water or sugar water or whatever, will it dissolve faster if I just take a whole chunk of it and put it in?
No.
No. How would it dissolve faster?
Little by little.
Little particles. So we could say, I might say manipulating the solute. So that might be by cutting it up into smaller pieces, grinding it up. I don't know, things like that. Things that make that process go faster. Have you ever made like orange juice from the freezer can? Have you ever done that before? Where you take the little juice can? Yes? No? I don't know if they even make that anymore. Oh, that makes me sound old. Okay. So they used to sell little orange juice like concentrates, they call them. Like they're frozen and you get them out of the freezer. And you have to undo it, and you pour it in your pitcher, and you add water, and you stir it up, and eventually it dissolves. But it starts as a frozen block. So now we've got like solid frozen things working against us, and a big chunk of our concentrate. So we could cut that up into smaller pieces, and it'd be able to go faster, right? That's a bad example if you guys don't know what I'm talking about. But we start with that big freezer can, and if we can manipulate that solute first, our dissolving process will go faster. Okay. All right. We're going to look at how to correctly make a solution. So I'm going to have you come back and kind of congregate in the lab back here. This is this concept of concentration is measured with a unit called molarity. Okay? So molarity is a measure of the concentration of a solution. How concentrated it is. We find molarity by taking moles of our solute over liters of our total solution. So I typically like to write this equation, not as long as that one, but I will typically write it as molarity equals moles over liters. Right? It has to be moles and liters. So we really, really need to make sure. Sometimes our volume is given to us in milliliters. How do we convert from milliliters to liters? Do you remember?
Don't you just divide by 1,000?
Right, I divide by 1,000. So if I have 1,200 milliliters, that would be the same as 1.2 liters, right? I divide that by 1,000. Are we comfortable with that conversion? That needs to be pretty straightforward for us, okay? So I have to have it in moles. I have liters of the total solution. Now, understand, this does not say liters of water. It says liters of the total solution. So it's volume of your solute and your water put together. Liters of solution. Okay, let's try this one. A 4-gram sugar cube is dissolved in a teacup that holds 350 milliliters of water. What is the molarity of the solution? Okay, they gave us here the formula for a sugar cube. For sugar, which is sucrose. Why do you think we need that formula? We need the molar mass because we need to convert from grams to moles. Okay, so that's our first step. We need to find moles of our solute. So we're going to take 4 grams of sugar, which they said was C6H22O11, and we're going to convert that to moles. Okay, we know moles gets the 1, and grams of this, C6H22O11, we need to go ahead and calculate that. So let's get periodic table out and calculate our molar mass. Okay, so we'll take 4 divided by 270. Is that what you had for your molar mass, I guess? Did you have about 270? Okay. So that means when we calculate that out, we have 0.0148 moles. Okay. Does that match what your calculation said? Okay. So I've got moles of my solute. I need my volume to be converted to liters. So how can I convert 350 milliliters to liters? What did we say we're going to do? Divide by 1,000. So I'm going to move that decimal to be 0.350 liters. Okay, so now if I want my molarity or my concentration, I come to my equation that says molarity equals 0.0148 moles divided by 0.350 liters, and I get 0.042. That would be my concentration. Okay, I want you guys using your calculators to plug in these numbers, not just watching me do that. Okay, on the next problems, I expect you to be plugging them in as we go. There's a big difference in watching me do it and you doing it yourself. Okay. Tell me, yeah, go ahead. There is, good. That's a good question. Our unit for this concentration is actually just our big M. Okay, so this molarity concept is both the label and the unit, right? We're solving for the molarity. And so when we say this, when we say that out loud, we would say it has a concentration of 0.042 molar. That's how we say it, okay? This has a concentration of 0.042 molar, okay? Or you could say its molarity is 0.042. So it's kind of a weird variable because it can go as both the variable and the unit, okay? But this is also known as its concentration, right? So we're finding out how concentrated that sugar is making the water. Okay. If I would add more sugar to that particular teacup, would my concentration go up or down? If I would add more sugar to my teacup, it would go up or down? It would go up, right? It becomes more concentrated because more sugar is added, right? I would have more moles, but my volume would not change. Right? Does that kind of make sense?
So this is how much the concentrate takes up of the whole solution?
Yeah, it's basically a measure of how much stuff is in there per liter, right? Per unit of volume. So
I could make this a percentage, and that could be like
we won't put it into a percentage, yeah, because we might not always be working with 1 liter, right? We're working with lots of different volumes. What would happen if I poured this exact tea into a bigger cup and added water? Would my concentration go up or down? down. It would go down, right? It would be like me diluting that solution, right? My volume would grow, but my moles would stay the same. So a larger denominator means a smaller overall answer. Do we agree with that math? Okay. All right, let's go ahead and look at the next one here. What is the concentration in molarity of a solution formed by mixing 10 grams of... Anybody know what that compound is called? H2SO4. The H is coming at the beginning. So what type of a compound does it have to be? An acid. Good. This one's called sulfuric acid, right? Because it comes from sulfate. So 10 grams of sulfuric acid with enough water to make 100 milliliters of solution. So we've got grams here. Where does that need to go? Can it stay in grams? No. If I want molarity, I need to find moles over liters. So I need to take 10 grams of H2SO4 and convert it to moles. So let's find molar mass there of sulfuric acid. Moles gets the 1. And our molar mass, tell me what we had with molar mass there. 98. That's what I had as well. Okay, so I'll take 10 divided by 98. And I get 0.102 moles. So is that it? Is that where I stop? That's my concentration? No, right? That's only the moles of my substance. If I want to find molarity, I have to take moles divided by liters. Okay, so is it going to be 0.102 over 100? Nope, it's going to be 0.102 over 0.100 liters. Okay, so I'm going to take that divided by 0.1, and I get a concentration of 1.02 molar. Okay, does that seem simple enough? Pretty straightforward, right? We're going to take our moles and divide it by our liters, but we have to really make sure that we're double checking our go around so you don't step on it. Well, you're already through. Okay. We need to make sure that we're really careful about our units, okay? If it's in moles, we can leave it. If it's in liters, we can leave it. But otherwise, we're going to have to convert there, okay? All right, let's try the next one. How many liters of a 3.4 molar isopropanol solution can be made with 78 grams of isopropanol? So what's different about this problem compared to our other ones? What'd you say?
We have the answer.
We don't have the answer, but we have the concentration this time. And we're searching for liters. We're looking for our volume. Okay? So that means if our equation is molarity equals moles over liters, we're looking for liters. Okay? We know the concentration is 3.4 molar equals moles over liters. So we need to find moles from this guy, don't we? We need to convert 78 grams of C3H8O to moles. I got my molar mass about 60. Does that match yours? Okay, and then when I convert to moles, I get about 1.3 moles. Agreed? So now I'm going to take that number of moles and I come in and put it over here where moles is supposed to go. Moles divided by liters. Okay, so this is where we come into a little bit of an algebra step that's tricky. Do you remember what we need to do if the variable we're solving for is right here on the bottom? Multiply what?
L.
Okay. So if I want to get L by itself, in the numerator, right? Because I want our equation to say L equals something. I need to multiply by L on both sides, right? I get it out of the denominator here by multiplying because it's in the denominator. And so whatever I do on the right-hand side, I have to do on the left. So now I'm left with L times 3.4 equals 1.3. How can I get L by itself at that point? Divide over 3.4, divide over 3.4. So now I'm left with the equation that says L equals 1.3 moles over 3.4 molarity. Agreed? What's the shortcut for that? Switch these two spots. Remember we did this early when we did density and some problems like that, right? The shortcut, if I'm looking for liters, I can just switch its spots with 3.4 molar, right? We did this early. We know the algebra behind it, but I can speed that step up by understanding these two are just going to switch spots. Okay, a lot of people, if they see this problem to begin with, if they see 3.4 equals 1.3 over L, they just multiply those together and think that's going to give me L. That's not going to work, right? I want L by itself in the numerator. Okay, so 1.3 divided by 3.4 gives me 0.382. And what will my units be for that one? Yeah, it's going to be liters. And if I had asked for that answer in milliliters, what would you do at the end here?
Times 1,000.
Good, multiply by 1,000, right? If I wanted it in milliliters, I could multiply it by 1,000. This is our last one. We're going to try this last one here. It says, how many grams of potassium phosphate would be needed to make a 1.32 molar solution in a container that holds 4.2 liters? Okay, so if my overall goal here is to solve for grams, what will I need to do? What will I need to get first? I need to find moles first, right? That's really going to be my question mark. So let's look at our equation. Molarity equals moles over liters. All right, I know my molarity is 1.32. 1.32 molar equals moles over 4.2 liters. Do I have to do any conversions with those?
Nope.
Looks like we're good to go there. Okay, so I know I have to solve for moles in order to get it to grams. What's my algebra look like here? How can I get moles by itself in the numerator? Exactly. This time I can just multiply, right? I just have to multiply on both sides by 4.2. So that would cancel it over here. And whatever I do on the right, I have to do on the left. So now I'm left with 4.2 liters times 1.32 molar equals the number of moles. And so I can just do the math there. And so the number of moles of my substance is 5.544 moles. But I want grams. Okay, before we move into grams, does everyone feel comfortable with that math and that algebra? Manipulating that triangle equation, right? When I call it triangle equation, I just mean because it makes a little triangle like that. Right? Everyone good with how we work through that?
Yeah.
Okay.
Does it matter how many decimal places I have?
No, it doesn't make a difference. Yep, good question, but no. So now I need to convert this to grams. But what do we not know right now?
The grams.
Correct. That's what we're looking for. What else are we missing? We're missing the formula, right? It says potassium phosphate, but I can't find the molar mass until I know what is potassium phosphate. Okay, so I'm going to give you like a 30-second head start. I want you to build the formula for potassium phosphate. We should be pros at this by this point. Yeah, what do you think? K3PO4. Perfect. Okay, because potassium is a +1 and phosphate is a -3. So we crisscross, that gives us K3PO4. Good. So this becomes this. And did you run the molar mass on it yet?
212.
I got 212 also. Potassium is 39. So 39 times 3 plus phosphorus, which I think is 31, and 4 oxygens. So I'll take 212 times 5.544, and I get, 1,175.3 grams. Okay, so that's a lot of compound that's got to go in. But you've got almost a 5-liter container, right? Like 2 pop bottles worth of containers. Okay. Any questions with that? Finding those concentrations? Okay. That's where we're going to stop.